Hello, and welcome to a Wednesday webinar from the International Center for Sustainable Carbon. My name is Benedicte, and I'm part of the communications team here. Our monthly webinars are based on our reports, which are available from our website, sustainable-carbon.org. Residents of member countries and employees of sponsoring organizations can download our reports at no charge after a one-off registration on the website. Please type any questions you have in the question box as we go along, and we will answer them at the end of the webinar. The subject for today's webinar is the role for coal in the hydrogen economy, presented by Dr. Chen Su. Over to you, Chen.
Thank you, Benedicte, for the introduction. Hello, everyone, and thank you for tuning in to today's webinar. In this webinar, I'll assess the opportunities and the impacts of low-carbon hydrogen production from coal with CCUS in a clean energy transition. Right, here is today's outline. I will talk briefly about the existing and new use of hydrogen and the projected future hydrogen demand. I will then look at the commercial production methods of hydrogen and compare them in terms of energy and carbon intensity, water consumption, land and material requirements. Next, I will examine the hydrogen supply issues with regional variations. The cost of hydrogen from different production methods are compared, and the coal's role in meeting the demand for low-emission hydrogen is discussed. And finally, the key messages for you to take home. Before I start, I'd like to clarify the definitions for different types of hydrogen used in this study. Renewable hydrogen refers to hydrogen produced using electrolyzers powered by renewable energy. Low carbon hydrogen is produced by coal gasification or natural gas SMR with CCUS. Both renewable and low carbon hydrogen are regarded as clean hydrogen. Hydrogen from fossil fuel-based production without CCUS is referred to as unabated hydrogen. Since the first hydrogen energy ministerial meeting in Japan in 2018, hydrogen has risen up the agenda in many countries. This table provides an overview of the status of national hydrogen strategies. Over 30 governments have introduced or are formulating hydrogen strategies, and more than 40 countries have released or are about to release hydrogen roadmaps for developing a hydrogen economy and the related technologies. Hydrogen is gathering unprecedented momentum around the world, and numerous companies are seeking to tap into hydrogen business opportunities. Currently, hydrogen is mainly used as a feedstock or reagent in refinery, chemical production, and steel making. Hydrogen can replace fossil fuel as a feedstock or as a fuel to decarbonize the hard-to-abate industrial processes such as melting and cement production, and facilitate different types of chemical reactions such as production of liquid fuels and the chemicals by hydrogenation of captured CO2, which potentially has a huge market. Hydrogen and hydrogen-based fuels can also be used in transport, including long-haul and heavy-duty transport, rail, shipping, and aviation, in power sector and in buildings for heating. Hydrogen uptake has already begun in transport and power sector with the fuel cell development, the pilot projects of injecting hydrogen into gas grid for home heating and the coal-fired hydrogen with fossil fuels for electricity generation. However, the adoption of hydrogen for new applications have been slow. The future hydrogen demand will depend on many factors, such as the policies, climate ambitions, the development of hydrogen technologies and the costs, and the competition from rival technologies. As a result, global hydrogen demand projections vary significantly due to differing underlying assumptions. These slides show the estimated hydrogen demand in 2050 in different scenarios by different researchers. It highlights the difficulty to quantify the future hydrogen use. But one thing can be certain is that the hydrogen demand will take off soon and will grow many times by 2050 from today's level. The question is how this demand will be met. There are 3 established technical routes for hydrogen production. Currently, natural gas reforming accounts about 62% of the 94 million tons of global hydrogen production. Around 19% of hydrogen is made by coal gasification, almost all unabated. The rest is mainly produced as a byproduct from refineries and the petrochemical industry. Less than 1% hydrogen is from water electrolysis. Depending on the technologies used, the cost and the carbon footprint of the hydrogen produced vary significantly. The energy efficiency of a hydrogen plant is influenced by several factors, including technology chosen, the size, feedstock, and the plant configuration. The energy efficiency and the energy intensity of each production method are generalized and compared here. It can be seen from this slide. The electrolysis is the most energy demanding, requiring significantly more power than hydrogen production from coal gasification and the SMR. CO2 emissions from different hydrogen production pathways differ widely, as shown in this figure on top, in this slide. The coal gasification has much higher carbon emission than SMR, but this can be brought down by adopting CCUS to a level that is comparable or even outcompete that of SMR with CCUS. CO2 intensity of electrolysis depends on the CO2 intensity of the electricity input. While electrolyzer powered by 100% renewable emit no CO2, electrolyzers driven by grid electricity that have a large proportion of fossil fuel generation would result in higher carbon emissions than directly using natural gas or coal for hydrogen production. Similar trend have also been reported by the IEA and Hydrogen Council. Water is consumed in hydrogen production processes as the feedstock and for cooling. The processed water must have high purity, which generally requires pretreatment and consumes additional water. This slide compares the water consumption of different hydrogen production methods. Although the value from different studies differ significantly, the general trend is same. Water consumption of coal-based hydrogen production is comparable to that of electrolysis and is twice as high as that of SMR, and it does not increase by adding carbon capture. The footprint of hydrogen plant with different pathway is compared in the table on top of this slide. It shows that electrolysis hydrogen plant has a footprint comparable to that of natural gas reforming with CCUS and smaller than the footprint of a coal-based hydrogen plant with CCUS. However, renewable hydrogen production requires sufficient land to host the wind and solar generation capacity. When taking into account of the land requirement of a renewable power plant needed to drive the electrolyzers, the picture changes drastically. The bottom figure compares the land area required for production of 1.76 million tons per year of hydrogen from coal or gas with CCS and electrolyzers powered by renewable electricity. So it shows renewable hydrogen production needs substantially larger land areas. In addition, construction of solar and wind power plant requires a great deal of materials. This slide compared the material required for coal and the natural gas combined cycle power generators and for solar PV and wind power generator. Solar and wind power plants use significant quantity of cement, concrete, glass, and steel. Production of these materials contributes to substantial CO2 emissions. Apparently, renewable and low carbon hydrogen production all have direct or indirect impacts on environment. Analysis of life cycle environmental impacts show when best available technologies are adopted, low carbon hydrogen from coal and gas could have a similar or slightly larger carbon footprint compared to the renewable hydrogen. Therefore, low carbon hydrogen from coal and gas can support the clean energy transition. Besides producing it, technologies and the infrastructure for storing and transporting hydrogen will be critical for large-scale hydrogen use. Hydrogen can be stored and transported by various means, either in a gaseous form under pressure of 35 to 70 megapascals, or in a liquid form at temperatures below minus 252.8 degrees C. An alternative is to convert hydrogen into a hydrogen carrier, which is liquid at ambient temperature and pressures, such as ammonia, so it is easier and cheaper to transport or store. Ammonia is a well-established hydrogen carrier with a volumetric energy density nearly double that of liquid hydrogen. Ammonia can also be combusted directly as a fuel in some applications without needing reconverted back to hydrogen, reducing the related energy loss and the costs. Ammonia is already an internationally traded commodity, and the infrastructure is in place. However, there is the energy penalty in conversion and the reconversion of hydrogen and the added costs. This means less hydrogen is available to the end user if the hydrogen were to be used to provide the energy required by the conversion processes. The cost effectiveness of various hydrogen transport options is determined mainly by distance and volume. The low energy density of hydrogen means it can be very expensive to transport over long distance. This slide shows the estimated cost of hydrogen transmission via different modes. For long distance transport, shipping will be cheaper than pipelines. Currently, it is only possible to transport relatively small amount of liquid hydrogen by ships, and the existing infrastructure for hydrogen storage and transport is lacking. Therefore, in the near to medium term, the scale of long-distance hydrogen transport will be limited, but international trade and the transport of hydrogen in the form of ammonia will increase. Due to the difficulty and the high cost of hydrogen transport, many new projects will be developed in the industrial cluster with end users on site or close by to minimize the cost. This will require the production of clean hydrogen from diverse sources linked to the different available resources in different regions. For countries heavily dependent on coal, such as China and India, hydrogen production from coal with CCUS will be vital to meet their increasing domestic demands. For other countries have abundant renewable and fossil fuel resources, such as Australia and the US, coal could provide a source for a cost-competitive low-carbon hydrogen production for domestic and international markets. Europe and Japan will be a major demand center for clean hydrogen, but are lack of resources and will be hydrogen importers. Middle East countries have enormous renewable and fossil resources and could become a major player in clean hydrogen supply. Meeting the targeted short to long-term demand for hydrogen will be massively challenging, requiring rapid scaling up hydrogen production capacity. In most countries, there is a big gap between the installed and the planned renewable hydrogen production capacity and the required capacity to meet the government's targets. Developing renewable hydrogen production also faces other challenges, such as the insufficient renewable power generation capacity to support the large scale of renewable hydrogen production while meeting the direct electricity needs, the electrolyzer production capacity limitations, and the supply issues of some key materials for electrolyzer manufacture. This means that the global demand for clean hydrogen cannot be met by renewable hydrogen production, at least in the near to medium term. Therefore, low carbon hydrogen production from coal and gas with CCUS is essential to bridge the gap in meeting the demand. In addition, hydrogen is much more expensive than fossil fuels it is to replace. Hydrogen production from coal with CCUS has a significantly lower cost than renewable electrolytic hydrogen, typically by a factor of around 3, as shown in this slide. For countries with abundant coal but limited gas resources, such as China and India, hydrogen from coal with CCUS will have the lowest cost compared to hydrogen from gas with CCUS and renewable hydrogen. This economic advantage will continue to 2030 or beyond. Therefore, hydrogen from coal with CCUS can improve the economic viability of clean hydrogen use, enable its early and wider large-scale deployment, and facilitating the transition towards renewable hydrogen use in the longer term. For coal-dependent, large hydrogen-producing and consuming countries, such as China and India, coal provides not only the cheapest source, but also a secure and reliable supply for hydrogen production. For coal exporting countries such as Australia, Indonesia, and the USA, producing low carbon hydrogen and its hydrogen-based fuels such as ammonia from coal can offer a suitable replacement for the current income from fossil export and provide the end users with options of clean hydrogen at low and stable prices. As renewable hydrogen needs vast area of land to host the wind and the solar power generation capacity, which can be an issue in some areas, especially in densely populated countries. For regions where low-cost land or excellent renewable resources are not available, but coal and carbon storage sites are, low-carbon hydrogen from coal with CCS will clearly be the best option. So this led to the key messages from this study. Hydrogen from coal with CCUS can have a low life cycle greenhouse gas emissions that are comparable to renewable hydrogen and outcompete hydrogen from gas SMR with CCUS. So it can support a clean energy transition. The global demand for clean hydrogen cannot be met by renewable hydrogen production, at least in the short to medium term, and therefore low carbon hydrogen from coal and gas with CCUS is essential to fill the supply gap. Hydrogen from coal with CCUS has a significantly lower cost than renewable hydrogen and can improve economic viability of clean hydrogen use, enable its early, wider deployment, and facilitating a transition towards renewable hydrogen use in the longer term. Hydrogen production will mainly be a local business requiring different resources available locally. For emerging and developing economy that depends on coal, coal is indispensable in providing a secure, reliable energy supply and an affordable source for clean hydrogen production. So this is the end of my presentation today, and thank you for your attention. Now let's see if there are any questions. Right, I've got some questions here. A pilot project was carried out to transport liquid hydrogen from Australia to Japan by shipping. Do you know what is the final total cost of hydrogen? How much hydrogen was borrowed off during the journey? Well, the second question, as far as I know, the liquid hydrogen was stored in a special vessel which kept in the chamber, which is cooled on the below the minus 252 degree. So there was the boiling off of hydrogen is minimal, but it's very energy intensive. So it does consume quite a lot of energy to do so. For the cost, there isn't any information available. I know the the research is carrying out, conducting this project, have been evaluating the economics of transporting long distance of liquid hydrogen, but no, there isn't any information available on that. The second question is, now the gas prices are record high, and so is the cost of hydrogen from gas SMR. The cost difference between renewable hydrogen and hydrogen from MSR with CCS will be narrowed. How do they compare now? The Argos is doing a regular estimates of the hydrogen production using different technologies based on the up-to-date gas and coal and the electricity prices, and they publish the results weekly or fortnightly, but on the regular basis. So the most up-to-date evaluation of the production cost is available. They use very optimal assumptions for the cost evaluation of renewable hydrogen, so that renewable cost of renewable hydrogen are lower than actual current production costs. And even though their results show that low carbon hydrogen production from coal and natural gas is significantly lower than the renewable hydrogen production. Let me see any more questions. Renewable hydrogen developers assume that cost of electrolysis will halve as the industry expands and the production technologies develop. What impact would such a cost reduction have on your conclusions? Well, this is the general expectation that renewable hydrogen, renewable electricity cost will come down, which it has in the past by 80% or something. But it is now still expensive, And even, yeah, as I just said, even with the current high prices of natural gas and the coal, the estimation of the cost of low carbon hydrogen is still lower, significantly lower than the renewable hydrogen production. Any more questions?
Great, Chen. Thank you so much. No, I think that's it. We don't have much more time today, but this is very fascinating, and I'm sure we'll learn more once the report is done. And
Okay.
all that's left for me to say is the slides from this webinar will be available to download shortly from our website. And our next webinar from us will be on the 18th of January on global status of bioenergy with carbon capture, BECCS, and will be presented by Dr. Jenny Jones. Thank you all for joining us today, and goodbye.